All right, so in this video, we're going to be looking at conducting contingency table tests. So typically, this would be a chi-squared test of independence. We're also going to look at sort of the non-parametric version for particularly sparse versions of the table in order to assess if the numbers are particularly small. There are permutation tests that you can do as well. So we're going to look at some of those, but this is all based on data that is in a contingency table. So we're going to start by entering the data for our observed table into R. Now, when you enter the table into R, don't enter the column sums or anything like that, only the sort of bare data that's inside the individual categories. So we're going to create our observed table. And we're going to build it as a matrix and from some vectors. So in this table, we have gender and sporting preference data. So the first set of values are for the women, and the three sports are archery, boxing, and cycling. And then we have the men in the same categories. And the size of our matrix is going to have two rows, men and women, and it's going to have three columns. And we're counting by row. So do the rows and then jump, one row, three columns, then jump down to the next row. That's what this means. You could spell out true, or you could just say T for the Boolean. And then we're going to label our rows and columns. So row names of our observed table. And then we're going to list these in a vector. And then column names of the observed table. And again, list in a vector. You can do them with single quotes or double quotes. And then we can print the resulting table. And so we see it's labeled. So it's always a good idea to look at the data after you've created it in R to make sure that it matches the data that you originally had in your original problem. Now, once we have this in tabular form like this, then we can conduct a chi-squared test on it. Now, the default assumption here for the chi-squared test is that it will conduct a test of independence. You may want to look at the documentation to see if there's other kinds of tests, such as tests for homogeneity or other kinds of chi-squared tests that can be done also on this table. But the default, when all you enter is the table value, is the test of independence. So here's our chi-squared test, and we have our chi-squared value and the degrees of freedom and our p-value. This is a very small p-value. This is strongly indicative of the fact that based on this data, men and women do have very different preferences for sports. Now, we can also do the Fisher exact test. And again, the Fisher exact test is a non-parametric version of the test of independence. It is normally preferred for data where you have very small counts, so not really this particular scenario, but you can do it on this particular data set. So this is something that's in the stats package. And then Fisher.test. And again, we just have to plug in our observed table. And it's going to run it, and we get a similar p-value. It's a little bit lower, but it's same order of magnitude. And again, this is assuming that the the expectations for the categories are unequal. So this is testing two-sided as opposed to one-sided. Sometimes the Fisher exact test for count data is also used when you have it's a version of the test for proportions. If you have two proportion tests, that's essentially what they're doing. But in this case, we're doing it on more than two. Now, we can also do pairwise proportion analysis to see if some of the levels of the variables are different from each other. So this is similar to when we did an ANOVA, we did a pairwise Wilcoxon test in a previous video. Here, when we look at a big contingency table, we could say, well, maybe the proportions in one column are different or similar than another column, and we can look at all of those paired comparisons. So we're going to pull this in from another library, not down there though. This is the R statics package. Again, if you have never used this before, make sure that you install it. And then this is the pairwise Fisher test. And for this, we need to convert it to a matrix, our observed table, because that's the input that it's looking for. And then also we're going to specify, since we're doing multiple tests, we're going to specify the pairwise adjustment method. And again, there are different methods that you can use. You will check the documentation for which methods are available and which one that you want to use in this particular context. And then if we run that, again, now this is going to output as a tibble. A tibble is just a data set that is used in the tidyverse, a data frame type. So don't be intimidated or bothered by that if you haven't been using the tidyverse very much. But basically, it's going to, again, compare the two groups group by group. So archery to boxing, archery to cycling, boxing to cycling, and given the p-values. And so here they're telling us the p-values for archery and boxing and archery and cycling are statistically significantly different, but that the difference between boxing and cycling is not statistically significant. So remember this, again, in some ways it's like an ANOVA in the sense that it's doing proportions. It's comparing the proportions collectively, are they different? And by doing the pairwise Fisher test, you're essentially pulling out the comparisons pair by pair and saying, are these pairs different? So we had 3 initial groups for archery, boxing, and cycling. And so now we're asking ourselves, again, not just are they all collectively different, is there any difference between them? But now, is it specifically this comparison or this pair? Now, you can also conduct permutation tests on your tables. So doing permutation tests manually on contingency tables like this work a little bit differently than doing permutation tests on like sort of t-test type data or Wilcoxon test type data. And so for this, we're going to import another package. So this is a package for non-parametric statistics. And this one comes with a permutation test on a table. And we're going to specify our observed table. And we're going to specify the number of samples we're going to take. And I'm going to say 10,000. And the results that we get, the chi-squared test statistic, we observe the p-value obtained from our simulation. And remember, essentially, we're saying that all of the variables are independent of each other. And here we're saying that in at least one circumstance, the variables are not independent of each other. So again, we get a similar result here to what we got earlier, although the p-value is much lower than we had when we did the traditional chi-squared test. Now, before we walk away from this, what we're also going to do is we're going to look at ways of visualizing our two-way tables, because sometimes that is also quite useful. And so for that, we're going to import one more library. This one's called Mosaic. And from this, we can actually create a plot, a mosaic plot of our contingency table so that we can visualize it. And we're going to put a title on it. And then if we run it, what we get is essentially the counts in each of the categories are turned into proportions, and they are plotted on our chart here so that we can visualize the differences rather than looking at the raw numbers. And so here it's easy to see that men prefer archery less than women. They prefer boxing more, and they also prefer, according to this, cycling more, although these cycling graphs, these cycling data is more similar in the two groups. So again, it's just another way of providing visualizations for our data. Now, there is one other kind of chi-squared test that we can sometimes conduct, and that is, we can also use that same chi-squared function for, and that is goodness of fit tests. Now, we have to do a little bit more work for goodness of fit tests than for the chi-squared test, the test of independence. We don't just have to put the data in the table. We have to also specify the expectations that we're comparing things to. So here we're going to create one list of a vector that includes the results, the counts in each of our bins. So maybe we have 5 categories, 53, and we expect a certain likelihood of being in each of the categories. Now, when we calculate these by hand, typically our table of expected values or our list of expected values is also going to be counts. So we would take this total sample size in our observations, we would multiply them by our corresponding probabilities, and then just put those counts in our list of expected values in order to do the calculation. Now that process is going to be done inside R. And so all we have to put in this expected list are the probabilities. Now, in this case, we are testing to see if the observations are uniform or sufficiently uniform. So we have 5 categories, and the probability of being in each category is exactly 1/5. And then we can conduct, again, that chi-squared test on our 2 vectors. So we would specify observed, and then we would specify the probabilities in our expected table, or our expected vector. And if we run that, Observed, apparently, I didn't enter this. There we go. What happens, you have to make sure you run these things. And we get a p-value of 0.359, which tells us that, again, our expectation, our null hypothesis for this goodness of fit test is that the observations do fit the distribution that we put into the expected table or the expected vector. So in this case, that they do fit a normal distribution is the null hypothesis. And then what we would be looking for is statistically significant evidence that it fails to fit in that distribution. And so this p-value indicates that we are unable to reject the null. This is sufficiently uniformly distributed. It does not suggest that any of the categories is different from evenly distributed, except by random chance. Now, if you're modeling a more specific probability distribution, you would have to know what the probabilities were in each of the categories. So it's not only a uniform distribution. You might have a binomial distribution or you might have a normal distribution. And then depending on how you binned your data for this test, then you would have to calculate the corresponding probabilities for that and then enter those into your expected table.